Hi students, in our previous video we have discussed about a short overview on our deadlock systems. Okay, so in this video we will move our next topic on same the deadlock. We have just discussed about the conditions for deadlock. Then we will discuss some of our avoidance and detection, recovery, all these techniques in this video. First of all, discussing about resource allocation graph. Okay, uh, here is something given. Okay, we have given the process and the resource name as vertices, and these are the edges. Okay, these are the edges. Okay, and before we discuss, if the arrow mark is from a process to resource, then the process is requesting the resource, while if the arrow mark is from resource to process, then the resource is allocated to the process. Okay, this is simple. Okay, in here something given. Okay, here is P. P is set of processes, these are vertices. Then R is a set of resources, these are also vertices. E means our edge. Edge means process P1 to R1, then P2 to R3. Okay, then R1 to P2. Okay, all these types of, these are the part of resource allocation of graph. Then here is something written: one instance of resource type R1. Okay, one instance. What do you mean by instance? Okay, sometimes the students may confuse that what is the instance of resource. Okay, I will if I am saying that I need a printer as a resource, I need printer as a resource. If there is one printer, then instance is one. If there is multiple, there is two printers, then there is two instance. If there are three printer, there is three instance. Okay, instance means the availability of resource. Okay, availability of same resource for different time. For availability of same resource, but number is multiple or single. Okay, then next move towards here we can discuss. Let's see the graph, see the diagram. Okay, here is our process P3. Have allocated the resource R3. P3 don't need any other resources, so the P3 can execute it successfully. Okay, I'm just marking a blue that P3 is easily executed. Then after P3 terminated, the R3 is free. Okay, R3 is free. Then the P2 have R1 and R2, while P3 is requesting for R3. P2 is requesting for R3, and after our P3 execute, R3 is available. Okay, so the R3 is allocated to our P2. R3 is allocated to our P2. Okay, R3 is allocated to our P2. Then P2 also executed. P3 already executed, P2 executed. Then after P2 executed, R1 is available and R2 is also available and R3 is available, while our P1 have already the R2 resource. P1 held the R2 and P1 are requesting for R1, and R1 is already available, so P1 can easily execute. Okay, here is no condition for deadlock. Okay, this is the resource allocation graph or resource allocation diagram. Here is another graph. Okay, here is P3. Okay, P3 requesting for our R2 and P3 already holding the R3. Okay, you should have to remember the four conditions of our deadlock system or deadlock. Hold and wait is the one of the conditions. Okay, P3 is holding the R3 and waiting for the R2. Okay, like that. Our P2 have the R2 and waiting for the R3, waiting for the R3. P2 holding a resource and waiting for another resource. P3 holding a resource and waiting for another resource. Okay, this is creating a cycle. This ultimately create a deadlock. Okay, you can easily check this cycle also. How our P1 hold R2 and requesting R1. Okay, and our P2 hold R1 and P2 hold R2 also. Okay, if our P2 executes, then our R1 will be free, and P2 already a part of deadlock system. Okay, so R1 never be free. Okay, so this is also a deadlock system. Okay, here this is a deadlock system. Okay, next move. Here is another graph. One is here resource allocation graph with a deadlock. Okay, here is the cycle, deadlock cycle present, and then here is also another example, a resource allocation graph with a cycle but no deadlock. Okay, here is a cycle but no deadlock. Okay, let's figure out. Here is our process P2. Okay, P2 have our R1 already allocated to P2. So P2 don't need any another resources. P2 can easily execute. Then our R1 is one instance of R1 is available. One instance of R1 is available. Okay, this is available while the P1 is requesting for this. Okay, P1 is requesting for this. So if this resource is allocated to P1, then P1 also executed. Then after P1 executed, this R2 is also available. Okay, then P3 have our R1 one instance of R1 and P3 are requesting for one instance of R2 while our this one instance is available. So our R2 also allocated, so P3 also executed, and then P4 have already allocated instance of R2, so P4 also can execute. Okay, this is there is no deadlock. Let's move to our cyclic nature. Okay, but P3 is holding a resource and requesting for another resource, and like P1 is holding a resource, okay, and requesting for another resource. This is cyclic, but no deadlock found because other three conditions doesn't available here. Okay, then here is our method of deadlock handling. Okay, how to handle deadlocks. Okay, let's discuss. First of all, handling deadlock have some methods. One is deadlock prevention, means how to prevent our deadlock. You have already known about polio. Okay, polio is a preventive. Okay, like that we have to take some steps or prevent steps, take some preventions before deadlock. Okay, then our deadlock avoidance, how to avoid the deadlock, then another one is how deadlock detection and recovery, how to detect the deadlock and recover the deadlock or free the system from the deadlock. Then there is a ostrich approach. Okay, ostrich approach is very much easy. Okay, just ostrich approach, ignore the deadlock. There is a myth that when the ostrich feels there is some danger, he hide his face in the ground, simply uh, ignore the danger or don't see the danger, ignore. Okay, this approach is uh, also a deadlock handling process. Why we use the ostrich approach? Because sometimes the handling of deadlock is more costly to manage the system or unnecessary. This cost is unnecessary. while we are using some personal devices, maybe the deadlock is not that much important, or you can simply restart the system. Okay, that's like. Next, move to our deadlock prevention method. Elimination of mutual exclusion. Okay, mutual exclusion means there must be one resource which is in non-shareable format. Okay, which is non-shareable format. Okay, although mutual exclusion cannot be eliminated, but there is software methods, very software methods which sometimes work well, but never give a great performance. Elimination of mutual exclusion simply it's not possible, but sometimes it's possible through a software implementation. Okay, then elimination of hold and wait. Okay, elimination of hold and wait. In our hold and wait condition, what happen, the process have to wait a resource and then wait for a resource which is hold by another process. Okay, here elimination of hold and wait means the process have to either wait all the resources or no resources. Either it's hold all the resources and execute, if not then no process will be hold. Okay, and then elimination of no preemption. Okay, elimination of no preemption. We simply no preemption means we can forcibly take out a resource from the process. Okay, elimination of no preemption means we can forcibly take out a process, take out a resource from the process. Okay, this is elimination of no preemption. Then elimination of circular wait. Okay, elimination circular wait means there should be maintain some order. Okay, there should be maintain some order of the resource, how the resource is allocating or deallocating. These are, it should be in a order of increasing or decreasing order. Okay, is also written the last concern, the circular wait can be denied by imposing a total ordering on all the resources types, then forcing all the processes to request the resource in order. Okay, this strategy imposes a total ordering in the all resources types. Okay, if you think that how the ordering occurs, we have to order that first you have to access R1, then you have to access R2. This type of methods. He can't access the R2 before R1. Okay, you have to first access R1, and then you will done your work, then release the R1, then another one or the same one can access the R2. Okay, this is our deadlock prevention method. Deadlock prevention method. Okay, then deadlock avoidance. Deadlock avoidance. Okay, how to deadlock avoid. Okay, there is a safe and unsafe state. What is safe and unsafe state? First of all, a safe state means, okay, from the graph you have to understand that unsafe state means if there is a unsafe state means there is a you just think there is a order of process. Okay, or a pathway of process. If in the pathway of process or pathway of processes, if a deadlock may happen, then this is in unsafe state. Okay, in the sequence of process, if there is no deadlock, then this is a safe state. Okay, simple. Here is written a system is said to be safe state if there is safe execution sequence. Okay, execution sequence means in our, okay, in this graph we can just I am just writing the safe sequence. Okay, safe sequence means we have first execute our P2. Okay, we can also execute our P4, then P2 and P4, this is free. Okay, then this is free. Okay, then P1, then P3. Okay, this is a safe sequence. Okay, also can P4, then P2, then P1, then P3. Okay, these are all safe sequence. Okay, in this sequence, if the sequence don't have any a deadlock condition in the sequence, there no chance of deadlock, then this is a safe state. Okay, safe sequence also called. Okay, if there is a chance of our deadlock, there is chance of deadlock, then this is unsafe sequence. Okay, then here is a resource allocation graph algorithm. Okay, we have already discussed about the resource allocation graph. And then here is our bankers algorithm. It's a bit important, how it occurs. Now let's move some text. Okay, it's a resource allocating and deadlock avoidance algorithm developed by Dijkstra that test for safety by simulating the allocation of predefined maximum possible amount. Okay, a simple I am telling the summary that here is matrices or tables are maintained that stores the data that how many resources are allocated, then how many resources needed by the process, then how many resources are available. All these are maintained, and by the maintaining, here one thing is found that which process we can found which process is now execute with these available resources. Okay, all uh, this is our bankers algorithm. Means we have to just uh, took some matrices and we have to store the values or the details in the processes. Means how many resources allocated to the process, how many resources needed to the process, then how many resources available at the same time. All this. Okay, let's move some example. Mm, this is our maximum resource available. Okay, when 7 instance of A is available, then 5 instance of 3 is available at the time. Okay, then available resources, one is 3, then 3, then 2. Okay, all this. Then this is allocation or allocated resources. P0 have 0A. Okay, then 1 instance of B and 0 instance of C. Okay, while our available resources 3, 3, 2. We can easily that give to A and give to C. Okay, then P0 can be. Okay, this is already allocated. Okay, here is some table of need, how much the A need, how much the A need. Our P0 need 7 instance of A, then 4 instance of B and C 3 instance. Okay, and our P1 need 1 instance and 2 instance of B and 2 instance of C, while P2 need 6 instance of A and don't need any other. Then P3 need 1 instance of B and 1 instance of C. Then P4 need 4 instance of A, 3 instance of B and 1 instance of C. Okay, from the available resource we can relate this. Simply we can execute the P1. Okay, P1, then what 1 instance of A will be given, then 2 instance of B will be given. Okay, then 2 instance of C would be given. Okay, then P1 successfully executed. Okay, then P1 successfully executed. Then the P1 have the resource 200. Okay, will be added to this graph. Now this is 5, 3, 2. Okay, okay, then 5, 3, 2. After 5, 3, 2, we can execute P3. Okay, because 1 instance of B and 1 instance of C can be selected here, can be allocated to P3, and P3 can executed. Okay, then after P3 executed, the P3 resources P3 hold that can be released. Then this is added to this. Then what happened? Okay, then this 7, then 4, then 3. Okay, this is how we calculate in our bankers algorithm. Okay, we will discuss some numericals about bankers algorithms in some next topic. Okay, this is our deadlock detection. Okay, how we detect our deadlock. This is single instance of each resource type. Then this is several instance of each resource type. Okay, this is our deadlock detection. How to detect the deadlock. Okay, next move. If all resources have only single instance, then it can define a deadlock detection. Okay, I mean, if just simple that if there is a single instance of every resources, then there may be higher chance of deadlock. Maybe, not sure. Okay. That uses a variant of resource allocation graph. It is called wait for graph. It can be drawn by removing nodes of type of resources, collapsing the appropriate edges from simple. We are drawing some resource allocation graph. Okay, and from the resource allocation graph, we can easily find there may be a chance of uh, deadlock or not. Okay, when several instances of resources can also the resource allocation graph help. Resource allocation graph also help. Okay, same like using the resource allocation graph, we can define that. Okay, here's some example already in our. Okay, this is our several instance deadlock detection. Okay, we can calculate is there any chance of deadlock or not. Okay, like that. Then next move to our recovery from deadlock. Okay, we detect our deadlock, then we will go for the recovery. Okay, how can we recover? First of all, one process termination, then one is resource preemption. Okay, simple thing. That process termination means killing the processes. Okay, after killing the processes, maybe the resources held by the process may be released. Then maybe the deadlock is about to end. Okay, then resource preemption means forcibly taking the resources from the process, not killing the process, but usually taking the resource allocated to the process. Okay, here is in process termination there is some once about all deadlock process. If there is two process creating deadlock, then eliminating all the processes. Okay, then another one about one process at a time until the deadlock cycle is in. Okay, first we are eliminating one process and then checking is there any deadlock available. If deadlock available, then killing another process. Okay, we are killing these processes one by one till the deadlock is eliminated. Okay, then here is our resource preemption. Okay, resource preemption means selecting a victim. Nothing that. Selecting a victim means just selecting a process and taking the resource which is allocated to the process. Okay, then there is rollback. The system or the operator must roll back the process to some safe state. Okay, and restart means after some time we have to select the process and restart. We should restart the process. Okay. Okay, all these are our deadlock. We have already discussed about deadlock in a previous video. These are our method of handling deadlock. Okay, thank you. We will discuss bankers algorithm, numericals, and cache memory algorithm numericals, and our CPU scheduling, and our disk scheduling. All these numericals in later on this channel. If you are liking this video, or if you are till present till now, then please do like and subscribe. Thank you.